Hi guys, welcome back. Let's talk about inferential decision making. I made the decision to sit down, so hopefully that's okay. Types of hypotheses. So we have the null hypothesis. There's no difference or no relationship is typically how it's thought of, and the alternative hypothesis, which is that differences are there or there's an effect or some sort of relationship that we see. So when thinking of inferential statistics, or in inferential testing, a conclusion about a target population is made based on sample data. Yeah. So you don't reject the null hypothesis, so the p-value is not significant, so it's not below the critical alpha, or you reject the null hypothesis, so the p-value is significant, it's below the critical alpha. You may be saying to yourself, Anandin, you've told me this 100 times. Why are you saying it again? Because it's really, really important in the context of what we're about to talk about, which is type 1 and type 2 errors, which you may not know about yet. So we hope to make the correct inference based on the sample data. So either we do not reject the null hypothesis, so we correctly retain the null hypothesis when there is no real difference effect in the population, right? Or we reject the null hypothesis, so we correctly reject the null hypothesis, which is the ability to detect when there is a real difference effect in the population, right? So fundamentally, if there's no effect, we want to retain the null hypothesis because that's what the null hypothesis is saying. If there is an effect, we're hoping that we can reject the null hypothesis, right? Because the null hypothesis, we should have evidence to reject it if there is an effect there. However, it's not always the case. We do make errors, right? There's type 1 and type 2 errors that can occur, which is that we incorrectly reject the null hypothesis or we incorrectly fail to reject the null hypothesis. So this is the nature of significance testing. We risk making an error. The errors are always there, and only thing we can adjust is the level of risk. So in type 1 errors is where you look at your result and they say they're statistically significant, so you reject the null hypothesis. But in actuality, if you had foresight and you knew what the true value is, you would actually be able to see actually there's the null hypothesis is true, right? So there's no difference or effect in the population. And type 2 errors is where you incorrectly fail to reject the null hypothesis. So you don't reject p-values greater than 0.05, you don't reject it, but in fact, if you had crystal ball, and probably shouldn't be using crystal ball analogies when we're talking about statistics, sort of antithetical to one another. But I try to do the imagination of saying if you knew what the population effect was, there is a difference or effect in the population, then you have made a type 2 error because you've not rejected the null hypothesis, you fail to reject it, but there actually is an effect in actuality. So here's a beautiful table, which let me help orientate you around it. Think of two columns, right? And the top is about reality. So there's two versions of reality, right? The first version of reality is the null hypothesis is false, right? So the null hypothesis is false. And so if you, in that reality where the null hypothesis is false, if you reject the null hypothesis, that's correct, right? So that's your power. We'll talk about that in a moment. But you've correctly rejected the null hypothesis, so you've detected your effect. Well, that's power. I think we've just talked about it. So that's what power is. Power is your ability to detect effect. And if you reject the null hypothesis in a version of reality where the null hypothesis is false, we've detected our effect. Now, if we, in fact, accept the null hypothesis in this reality where the null hypothesis is false, we've made a type 2 error, right? Remember, type 2 error, we failed to reject the null hypothesis. So we failed to reject, well, we should be rejecting the null hypothesis in this reality, but we haven't. So we've made a type 2 error. Let's take another reality. So scratch that from your brain. Think of your normal distribution or any distribution, and you have the null hypothesis is true in this case. If the null hypothesis is true, and you'd want to be accepting the null hypothesis, you want to correctly accept the null hypothesis, and that's what that fourth quadrant is. But if the null hypothesis is true, there's no difference in groups, or there's no effect, and you reject the null hypothesis, then you have made a type 1 error. And this is in relation to alpha. So in summary, that's type 1, type 2 errors. So you correctly accept null hypothesis, you correctly reject null hypothesis, or you falsely reject the null hypothesis, so your p-value is less than 0.05, even when it shouldn't be, because the true population value is actually the null hypothesis is true. So you reject the null hypothesis when it's true, so that's a type 1 error, and that's our alpha level. That's the level at which we're willing to accept a proportion of false positives. And why is it a false positive? Is because your statistically significant effect, so it's detecting, falsely detecting a significant effect. False acceptance of null hypothesis is when not rejecting null hypothesis when it's false, which is type 2 error, which is your power, your beta. Sorry, beta is your type 2 error. Yeah, and when you do 1 minus beta, that's where you get your power, right? We'll talk about that in a moment. Traditionally, emphasis has been on too much on limiting type 1 errors. People have really tried to focus on, well, we don't want to detect effects that are true that aren't really true or aren't really there. And not enough on limiting type 2 errors, and there's a balance that's needed. And I hope this is the diagram that sticks in your mind for a long time. And the reason why is it shows beautifully the relationship between alpha levels and beta and type 2 error beta levels, and also what power is. So if you can remember this diagram, you'll know all these concepts. So this is under the distribution here that the null hypothesis is true, and here's under the distribution that the alternative hypothesis is true. So this is the relationship between type 1 and type 2 error. And so moving the alpha level, you can see will change this beta level. And so let me explain. So under the null hypothesis being true, null hypothesis is true. If we reject it, because our test statistic is here, we've created a type 1 error. Yeah. And type 2 error is what occurs here on the left of here, right? So the type 2 error is under that when you have the not rejecting the null hypothesis when it is false, right? So you don't reject the null hypothesis when it's false. And so here we say, okay, let's take the null hypothesis to be false, yeah? So we should be rejecting it, but if our test statistics falls here, then we've actually created a type 2 error. We've not rejected the null hypothesis when it's false. Now, what I want to show you is this is the alternative hypothesis, or our ability to detect an effect, right? So everything on the right of this blue line, 1 minus beta, is actually, because under distribution, normal distribution, the area is 1. Everything on the right of that line is your ability to detect an effect, should an effect be there, right? So if 1 minus beta is your power, and so that's the relationship between alpha, beta, your type 2 error, and power, which is 1 minus beta here. And so if you can look at this diagram and understand what it means under the assumption that the null hypothesis is true, and when you incorrectly reject the null hypothesis when it's true, that's a type 1 error. And then if you accept the null hypothesis when it's false, right? So or don't reject the null hypothesis when it's false, or because you never really accept the null hypothesis. You either reject or fail to reject. It's confusing wording, but that's the nature of the thinking about statistics here. And then you've got the type 2 error. So the probability of correctly rejecting a false null hypothesis, right? So your null hypothesis is not true. Null hypothesis is not true. So what's the probability of rejecting that null hypothesis? We're given it's not true in the population. So for example, getting a significant result when there is a real difference in the population. Or in other words, when you're thinking of power, statistical power, what is your ability to detect an effect, assuming that the effect exists in the population? And so power is here, right? So in reality, the null hypothesis is false, and you reject the null hypothesis. You detect the effect, yeah, reject the null hypothesis, and the null hypothesis is meant to be rejected because, so you've detected it. So that's where power sits, yeah? And it's thought of as 1 minus beta, which is written here, 1 minus beta, correct rejection. So Desirable power, greater than 0.8. Typical power is often around 0.6 in social sciences, and power becomes higher when any of the following increase. Your sample size increases, your critical alpha increases, or your effect size increases. You can't really control the change in your effect size. You can control the change in your critical alpha. You can increase alpha, and that means you'll have a higher threshold to detect an effect. Remember that alpha and power are related, right? So if we increase alpha, we have a higher likelihood that we'll detect an effect, yeah? So we can increase the critical alpha, or you can change it from bidirectional to a unidirectional, like one direction test as well. Or you can increase the sample size, and all typically doing the top two, but often at times the standard is not to increase critical alpha because of these not well thought through rationale for, well, it's been done this way for so long of using a p-value of 0.05, we should keep doing that. And so the sample size is really the main lever that people pull when trying to increase power. But arguably, it's defensible to increase your critical alpha as well. So a study has a power of 0.8. What is the likelihood of a type 2 error? So a study has a power of 0.8. What is the likelihood of a type 2 error? Yeah, keeping in mind the area under a curve is 1. So if we're looking at type 2 error and power, 1 minus 0.8 give you 0.2. So that's the answer there for that question. So power analysis is ideally calculate expected power before conducting a study, a priori, based on estimated sample size, critical alpha, expected or minimum effect size from related research. So you look at the research that's there, you see what effects they found, and you infer what the power could be, and you conduct your analysis. You can also report actual power post hoc in the results. What was the actual power that's there? This is what it would look like if you use the most commonly used tool, which is G-Power, to detect power. And what I want to draw your attention to is that it asks you for questions about what your effect size is and what your alpha level is, and that's how it is calculating overall power, right? So it uses a combination of these points and also sample size. So you can change these numbers, and that allows you to determine what the power can be for your study. So it's not a fixed thing, it's actually quite fluid, and in terms of how, and it comes down again to justification, how you justify it based on previous research. Now, in some of my studies, I've not even done a power analysis because my power of the number of people I've had in my study has been upwards of 100,000, 200,000 in the UK Biobank. So there, the problem is actually the opposite. It's not that I don't have enough data to detect an effect. It's that I have so much data that my power is so great that I may detect a lot of effects that are really, really small. And it's up to me as a researcher to determine whether those are clinically meaningful or not. And that's really the converse. So you either have not enough people, and so you need to do power analysis, check if you have the minimum sample, or you have too much people, and so you need to use some justification to ensure that your analysis and your results make sense and are applicable to the broad population. So power is just the ability to detect an effect. Probability of detecting a real effect is statistically significant. You can increase power by increasing the sample size, increasing critical alpha level, or increasing the effect size. But increasing the effect size, the effect is what it is as well. So it's just theoretically thinking about the factors that influence power. So power at 0.8 is desirable, 0.6 is more typical, and can be calculated prospectively and retrospectively. So I've talked a lot about effect sizes. Let's have a discussion in detail about what is an effect size. What do we mean when we're talking about effect size? Well, an effect size is termed as anything that is a measure of strength or size of a relationship or effect. So what I'd love you to do is actually pause the video after I say this question and ask yourself, what effect sizes have we possibly looked at so far in this course? Are there measures that could have been effect sizes that we've looked at? And where p-value is reported, also present an effect size. So reporting and interpreting effect sizes in the context of previously reported effects is essential to good research. Yeah, so that is the context of effect sizes. Why do we use them? Well, an inferential test may be statistically significant, so the result is unlikely to have occurred by chance, but this does not indicate how large the effect is. So the effect may be trivial. And I gave you some examples previously in regards to numeric memory and how that could be statistically significant in a large data set, but not clinically meaningful. On the other hand, there may be non-significant but notable effects, especially in low-powered tests. So if you don't have enough power, there may be notable effects, but they're not statistically significant. So unlike significance testing, effect sizes are not influenced by n, right? So they're not influenced by the number of people in your sample. So what are commonly used effect sizes? The correlation is a commonly used effect size. As we talked all about the different thresholds that you could use to interpret a correlation. So R squared, semi-partial correlations, R, and coefficient determination, mean differences. So standardized mean difference, which is Cohen's d, the eta squared or partial eta squared. These are all terms that you may have been exposed to already, but seeing in terms of effect sizes. But effect sizes don't need to be too complicated. It's really when you talk about your study, what is the measure of effect? So, for example, say I'm interested in the difference in height between men and women, and I conduct a study and I do a t-test, I'm looking at the differences in height. I could have my effect size be something as simple as the centimeters difference between them, and say I see a 30 centimeters difference in statistically significant. My effect size is the mean difference between them. Right? It doesn't need to be standardized mean difference, but it can be, which is Cohen's d, because it allows you to give a magnitude of effect that's not relative to a scale. But when it's unstandardized, you can still have some interpretability about what that means. So is 30 centimeters difference meaningful? Or for example, if I was saying the effect size, if I'm looking at the impact of walking on lifespan, and I see the difference between people who walk regularly and people who don't walk is about 10 years, then in lifespan, then that 10 years is my effect size, right? So that's just the different mean difference between the groups. And so the effect size can be your regression, it can be your beta estimates from your multiple linear regression. Those can be your effect size. It could be your standardized beta estimates. Anything that measures the effect. Remember, the definition is a measure of strength or size of the relationship of the effect, right? So strength or size. So anything that measures the strength or size of an effect is an effect size. So standardized mean difference is the difference between two means in standard deviation units. You have a negative difference, zero difference is no difference, and positive is a positive difference. So a standardized measure of the difference between two means is D, which is mean 2 minus mean 1 over standard deviation, or Cohen's d or Hedges g, which is mean 2 minus mean 1 over the pooled standard deviation. So this is, these are also measures of effect. So I'm just trying to expose you to the different types of measures that are there. Cohen's measure of effect were small, moderate, or large, 0.2, 0.5, 0.8. Wolf says 0.25 is educationally significant, 0.5 is practically significant. Fundamentally, my thinking about this is that when it comes to whether it's practically significant, it depends on the area. It depends on the area that you're looking at, depends on the measure. And so you need to look into, is this measure meaningful for that area of research? So if your inferential test is not significant, you should still present an effect size as well as interpret this, because it could have come about by chance. So interpreting effect size, there's no agreed standards. It's ultimately subjective, which is where the justification piece comes in statistics. How can you justify that this effect should be there? And I really think that the burden of proof should be on the researchers to say, this is the effect. It shouldn't just be it's statistically significant. They should also have to justify that the effect size is clinically meaningful. And the best approach is to compare with other similar studies and use logic. So you may be asking yourself, what does this logic look like? Well, it depends on context. So a small effect size can be really impressive if, for example, a variable is difficult to change. So for example, personality construct. So if the effect is really, really small from an intervention, but it's a really challenging construct to change or variable change, then that's a meaningful difference. If it's very valuable in terms of life expectancy, like even a 1 year difference in life expectancy can mean a lot, particularly maybe for children who, if they have some disease and their life expectancy is drastically shortened. Again, relative, the 1 year means so much more than if it's for the average life expectancy that's 80. I think this puts some sort of relative sense of a year is not a year in all contexts. It depends on who it's applied to. So this is where the logic comes in. So and a very large effect size does not necessarily mean that there's any practical value. For example, if it's not related to the aims of the investigation, or it just is not meaningful. So for example, say you you do some intervention that increases the effect by fivefold. There's fivefold increase in the effect, but the number of people that would actually be in that category to benefit that effect is so small. It's like 1 or 2 people in the world. Then the fact that there's a fivefold increase for those people, maybe it's interesting to those 2 people, but for the large population, it may not be of relevance. So this is where we have to consider who our population and sample are. So power and effect size in psychology. So Ward examined articles in 3 psychology journals to assess the use of statistical power and effect size measures. So Journal of Personality and Social Psychology, Journal of Consulting and Clinical Psychology, and the Journal of Abnormal Psychology. They found that 7% of studies estimated or discussed statistical power, 30% provided effect sizes, the average effect size was medium, and current research designs typically do not have sufficient power to detect medium effect sizes. So their average effect size is medium, but their power that they're using is 0.8, and so they're not having sufficient power to detect that meaningful effect size and medium effect size. So this is published in 2002. Things have come along a long way since then, but I still probably every day I read research papers that focus on statistical significance, direction of effect, but not magnitude of effect, what the effect size is. So if there's anything you can take away from this, ask yourself the same question. It'll enhance your critical thinking of research papers immediately by asking the question of what is the size of this effect? Is it clinically meaningful? How is it measured? What is the scale of measurement? And all of these things in conjunction with the confidence interval and the p-value will help enhance your critical thinking of statistical studies, of any studies. So summary of effect sizes is that it's the standardized difference or strength of relationships. It doesn't have to be standardized. You can also use unstandardized. It's just the difference of, or strength of relationship. Inferential tests should be accompanied by effect sizes and confidence intervals. Common bivariate effect sizes include Cohen's d or correlation. Pearson's R are some common effect sizes that you'd be aware of. Excellent. So let's talk about confidence intervals. So probably I would say confidence intervals are one of the most notoriously, oh, I can't say that. That's a bit of a generalization. I would say notoriously misunderstood part of statistics, but actually p-values probably take the cake. But you now have a good understanding of p-values, significance testing, effect sizes, so that helps. But in terms of confidence intervals, it's very, very useful, but it's underutilized. It gives ranges of certainty or area of confidence. For example, a population mean is 95% likely to be between negative 1.96 and positive 1.96 standard deviations of the sample means, right? So that's the range of certainty that a confidence interval provides. That's how people typically interpret confidence intervals. But in fact, there's more nuance to it than that. What a confidence, and it's expressed as a lower limit and an upper limit, so you have a lower and upper limit of a confidence interval. But how to truly interpret a confidence interval is that if we repeated this study, say 100 times, many times, and constructed an interval each time, but using the same method, 95% of those intervals would contain the true parameter. So when you talk about your confidence intervals in your studies, it doesn't reflect that the true value is between X and Y, right? Which is what people often interpret it as noted here. But in fact, it's if we were to conduct this study 100 times or many, many times under the same conditions, using the same method, 95% of those intervals would contain the true parameter. Yeah, that's what a confidence interval means. Now, confidence intervals can be reported for beta unstandardized regression coefficients in multiple linear regression. It can be reported for means and also other effect sizes. So they could be used for a whole wide range of effect sizes and can be examined statistically and graphically using error bar graphs. So you may see this in plots where they have error bar graphs, and if the confidence intervals do not overlap, gives you a quick visual of saying that it's likely statistically significant, the difference between those groups. And so here's an example of a systematic review I conducted that was looking at differences in fat mass between pre- and postmenopausal women. And here I'm looking specifically at trunk fat percentage difference. And here, these are all separate studies. And what I'm constructing here is the mean and the confidence interval here. So that's the mean and confidence interval. And what I want you to see is that the sample size. As the sample size increases, the confidence interval gets very, very small, right? And so, and you can see as the sample size decreases, confidence interval gets wider, right? And so, and here, and for other reasons, it can get wide as well. And so, what I want you to take away, and you can see how this overall estimate is likely influenced by this large study here. But what I want you to take away is looking at this, is considering what these confidence intervals mean. So here, this confidence interval, really, if we were to take it as not a systematic review, but rather a normal study, it's if we were to repeat this study many, many times, 95% of those confidence intervals constructed would contain the true value. Yeah, so that's what a confidence interval is. So let's do some practice questions. If a multiple linear regression predictor has a beta value of 0.5 with a 95% confidence interval of 0.25 to 0.75, what should be concluded? Do you reject the null hypothesis or do you not reject the null hypothesis that beta is equal to 0? The key indicator here is, does the confidence interval cross 0 or not? Here, the confidence interval does not cross 0, and so you reject the null hypothesis. If it crosses 0, that means that of all the, when you repeat it many, many times, the true value could be 0. Therefore, you state that there's no difference, right? You don't reject the null hypothesis. Again, if a multiple linear regression has a beta value of 0.2, 95% confidence interval is between negative 0.2 and 0.6, so it crosses 0. What should be concluded? Again, the interpretation, if we repeat this study 100 times and compute confidence intervals, 95% of them will contain the true value, which could include 0. Therefore, we do not reject the null hypothesis, i.e. that beta is equal to 0. Which set of confidence intervals indicates the mean score is significantly different from 3? So here, you're trying to identify that the confidence interval for this other measure does not include 3. So look here and see which ones don't include 3. Hopefully, you can quickly see that that is C. Quickly see that it's C. And so that's what we see here. Okay, I'll stop. So that's the 95% confidence interval there. So what's the summary of confidence intervals? It gives a range of certainty when generalizing from a sample to a target population. If we repeated the study many times and constructed an interval each time using the same method, 95% of those intervals would contain the true parameter. That's what a confidence interval means, right? Confidence intervals can be used for means, betas, and effect sizes, other effect sizes as well. Means and betas are effect sizes as well. Can be examined statistically using upper and lower limits, or graphically using error bar graphs. Now let me just as a little bit of extension material, not accessible for this course, but I wouldn't be doing my duty as a teacher if I didn't show you what credible intervals were. And credible intervals are the Bayesian, I guess you could say the Bayesian equivalent to confidence intervals. However, in credible intervals, you can in fact interpret them in a very direct way, which is where you say there is a 95% probability that the effect lies within this interval. That's not the interpretation of a frequentist confidence interval, but credible intervals, you can say that. So in this example, this is a study that was looking at differences in dementia timeline for different groups. And for Alzheimer's disease, I found that there is a 95% probability that the true average time to dementia diagnosis for Alzheimer's disease lies between 3.03 and 3.72 years given the data in the model. So we can make direct probability statements using the credible intervals. That's unlike what confidence intervals are, which is actually this process of saying if we were to repeatedly sample. And what you'll find in many of frequentist statistics is this idea of repeated sampling comes up again and again, because that's really the concepts behind how they determine the true parameter within the population. So standard error, if you repeatedly sample and you get the standard deviations of the distribution, sampling distribution, you get the standard error. It's all through repeated sampling. Whereas here in Bayesian, it's a direct probability statement. So that's something to keep aware of. And if you're interested in that sort of interpretation, which is useful in a lot of contexts, then a Bayesian analysis would be the way to go. But not assessed in this course, but important to know that it's out there. Excellent. So in saying that, let's pause there and we'll come back and talk about publication bias. Have a break, stretch your legs, make a tea, and we'll come back and chat more about publication bias.